as Seven points out, we could also do cooling. So Newton's law of cooling is a kind of a neat thing. It should be noted that Newton's law of cooling is one of these fundamentally a model situations. Like, we're calling this thing a law, right? But really it's actually a mathematical model of cooling. It's not necessarily how cooling works in each and every situation. In particular, I believe this one breaks down kind of badly when we get towards absolute zero. Let's call that. But the idea works really well at room temperature. As long as the room is big enough and the thing that you're heating has a low, okay, fine. It works okay. It's okay at best. So, what does it say? You guys know Newton's law of cooling? What's it say?
Basically, the rate at which something cools is proportional to the difference in temperature between that object and the surrounding environment.
Something like this?
Yeah.
You guys all cool with this? Okay, so
Ha ha.
that wasn't meant to be funny. I'm sorry. I apologize. I hate fun. Okay, so what I would like to know is, do I have the signs right in my head? You guys see this? So this guy, what's T modeling? Like,
Temperature of the object.
okay, so that's what I'm thinking of as temp of object as function of
Time.
probably time. Okay, this guy is going to be dt d little t.
Might be the rate then of cooling.
Yeah, and this is the rate at which the temperature is changing, right? Okay, what's TE here?
Temperature of your environment.
Okay, and for the purposes of this simple exercise, I'm going to assume that the temperature of my object as it cools is not affecting the temperature of the environment it's in. Does that seem legit?
No.
I don't know, it depends, right? Like, Manya's got a cup. Can I steal your cup for a second? So, if you fill this with hot tea, right? Which it smells like it was at least at one point hot tea.
Yeah, but that tea cooled.
But it cooled, because of course it did. Did Manya's tea, as it cooled, appreciably warm the room? No, it said appreciably. Did it warm the room? Like, yes, absolutely. The room was slightly warmed by the cup of tea. You guys see that?
Yeah.
But how much did it probably warm this area over here? Like, this little cup-sized chunk of air, right, was warmed probably on the order of, what, maybe a 10,000th of a degree or something? Right? Like, not very much. You guys see that? Like, would it be a viable method for you to stay warm in your car overnight by bringing one hot cup of tea into the car? Probably not, right? Would it be a viable method for you to stay warm in your car overnight by bringing in, oh, I don't know, a half a kilogram of water warmed to 20,000 degrees?
Not very practical.
It's not super practical because it's really hard to keep that thing in a container, right? Because it wants to be gas. But it probably would warm the heck out of your car, at least for a while. You guys see that? And then we would have a second stage of cooling where your car is heating the environment outside of it, right? So this thing, right, does a nice job when you have a relatively reasonable object in a big space. Like, when your cup's in the world, this is a great thing because your cup is not going to appreciably warm the world. when your cup's in a container this big, it's not a good model. You guys see that? Okay, so how the heck could I try to solve this? Oh wait, I needed to get my signs first.
Yeah, there's that caveat that, you know, when the temperature difference is bigger, your cooling is your dropping of the temperature, so that's.
Yeah, so I just want to make sure I have this sign right in my
Yeah.
head. So T prime, right, should be when the temperature is higher than the environment, right? Like when this part's positive,
Yeah,
T prime should be
negative.
negative.
Only.
Okay, so I feel like the K could take care of that, right? I could just assume K is a negative constant. But that sucks as an assumption. I'm going to put a minus sign in here. You guys see that? Does this step have to be done?
No.
No. You could straighten this out on your own later.
If it didn't have a negative sign though, it would be heating up then, right?
K would just have to be negative,
Oh.
right? The constant of proportionality would just have to be negative, which is awkward. It's better if you can do these straightening outs at the beginning, but you don't have to. Like they'll come out in the end. You'll want to look at the limits of how your model behaves, and then you'll see that, like K, for instance, has to be negative. Okay. What I would like is to be able to come up with a guess for a solution to this thing.
I feel like it has to be an exponent plus something, like a shifted up exponential.
Yeah, it seems like it probably should be an exponential in here somewhere, right? Okay. So let me make a series of guesses. First guess. T as a function of t is, what's your first guess?
E to the KT.
Let's go with e to the kt. That seems like a good thought. Like e to the t is a good thought too, right? You're just going to pretty quickly find out that you need a k in there.
Yeah.
Okay, so what's t prime in this case?
K to the KT.
K e to the kt. Okay, so I should plug that in here, right? You guys with me? And I just want to see if it works. So my see if it works is t prime, k e to the kt, is that equal to minus k times e to the kt minus te? What category of thing is te? Yeah, it's a number. Crap.
Room temperature is absolutely. Yeah, that's.
Room temperatures. Oh god, let's not. I'm too confused. Yeah, stay away from zeros.
Yeah.
Okay. So what respects has my guess failed in?
Doesn't have a TE in it.
It doesn't have a TE in it, and also there's a negative someplace in there that seems to be problematic, right? Okay, so an improved guess, at least, would be t as a function of t is e to the minus kt. Right?
It'd be easier if you distributed the negative k to the other thing, right? And then there'd just be negative kt plus kte. That seems like that'd be pretty easy to do.
Yeah, that's not a bad idea, actually. That's that kind of up to algebraic manipulation, right? You guys see that? That's a good thought. Let me just try this with, and then we'll see where we're off. Okay, so t prime for this guy is going to be minus k e to the minus kt, right? And so if we plug everything in, we'll get minus k e to the minus kt, and we're wondering, is that minus k e to the minus kt minus te? And then we might notice, like, oh, hey, this stuff is minus k e to the minus kt minus te, right? And so I might say, like, well, hey, I'm good on this and that, right? You guys see that?
Yeah, it would be plus
Oh,
KT,
okay.
yeah.
No. I told you, up to good algebraic manipulation. None of this bad algebraic manipulation I have a tendency to do. Okay, so it seems like either K or TE has to be 0 for this one to work. Probably I don't know either of those things. So, how do you fix it? Good. Make another guess, right? So what else could you do?
Could you, yeah, that, the equation you have down there, that's where you're at, right? So, if you integrate that with that,
How about you subtract K times TE from your temperature function?
That seems like an idea. You guys with that?
Basically adding the constant, but that constant is.
Like we could try, yeah, so I'm with you about the integrating thing. Wait, what was your name?
Brandon.
Brandon. I'm with you, Brandon, about the integrating thing. That's a really good idea, but don't steal my next lecture, okay?
sorry.
So, let's try Manya's thing. That seems like a good idea. So where do you want to subtract it from? You
Okay.
just want to like take it off the temperature
Yeah,
function?
yeah.
That's a good idea. Okay, so we'll do e to the minus kt minus
K times TE.
k times te.
Yeah.
Okay, so when I differentiate, right, t prime of t, I get, so this piece is 0, right? And I get my minus k e to the minus kt. Okay, so now I should try substituting, right? So, seems like t prime, so is minus k e to the minus kt, is that, I need a minus k times e to the minus kt minus kte. Oops, that's t, and then I need still, what?
Minus
Yeah, I still need a minus te here.
We just get rid of that K on that minus.
You guys see that?
you can't so
Oh,
Where does that
you
go?
take the
It's like almost there.
you take
So-
the K out of the
Hang on. I think I've got 2 levels of questions. I have, are some of you asking where this crap came from? Okay, so this thing here, right, is t prime. You guys all with that? Like I took t prime, that's this stuff, I put it on the left-hand side because I have t prime on the left-hand side over here. You guys good with that? Okay, then I had a minus k. That is literally just the same minus k from over there. Then in here, in these parentheses, I have a, this whole business is t. You guys see that? Because that's what I said t
Right.
was. Is all on board with that? And then this dude here, where'd the minus te at the end here come from?
really nice.
That was because it was part of the original.
If we use just the plus TE, I think
Oh.
it'll cancel out.
Yeah,
Just
Yeah,
plus TE.
so we were good about like this adding or subtracting
Yeah.
something was a great idea. I just went a little overboard with it, right? So it seems like if it was just a, what do I need? I needed to cancel with a TE, right?
oh, yeah,
So I think just plus TE should do it.
yeah.
You guys all see that? Okay, so I think ultimately I'm getting a really good guess now, and it's T of t is e to the minus kt
Plus D.
plus te. You with me on that? Okay, now I still don't know where that constant goes. There's probably a constant in here someplace. Do you want to figure out how to find out where that constant ought to go? There's a slightly varsity trick here for figuring out where the constant goes. What should t of 0 be?
Zero.
That should be the initial temperature, right? You guys all with me on that? What is it if I plug 0 in here to this model that I've figured out?
TE plus 1.
E.
TE plus 1, right? Is that right? Is the temperature 1 above the environment? Could be. Is it always? Definitely not, because I haven't even specified what temperature system I'm in, right? Like this should be true in Fahrenheit and in centigrade,
It's not always
right? It's not 1, but it is 1 times the difference above. You guys see that? So really I should be putting something right here to turn that 1 into the appropriate thing. You guys with me on that? So if I wanted to make a better guess, and I'm going to kind of skip ahead here and actually make a better guess. So I do T of T is, and in here, I need something so that when I plug 0 in, I get the temperature of the object to start with.
T naught.
So T naught, because when I plug 0 in now, I'm getting T naught plus TE,
Oh, T naught minus T.
T naught minus TE. You guys see that? Okay, now we should check. Right, so we went all out, we got our guess here. Hopefully this thing works. How do I check whether it works or not? Yeah. So this is the question, and this is a question that's going to appear on your homework a bunch of times. So the question I'm answering is this thing a solution to this? You guys all with me on that? That's actually the question I've been trying to answer with every guess, right? Like I've been guessing, and then is that a solution? I've tried to plug it in the orange, and no. So I guess again and try again. So let me do this one. So really careful, because I want to make sure we got this right, because this would be important. And if we get this wrong, things just won't cool the right way. I'm just kidding. The world doesn't care if your model's wrong.
But it's a law.
Yeah.
Everything's just gonna follow that
So
law.
I need to calculate what?
T prime.
I need to calculate T prime. So T prime of T should be, whoa, T0 minus TE is categorically a constant. So leave that alone. Okay, then what else?
Negative K.
You get a negative K that drops out of the power, and E to the negative KT. And I said this dropped out of the power. What was that saying? What was that really coming with? It's not the power rule. It's the chain rule, right? You guys see that? I'm not like dropping the power and then decreasing the power. I'm doing the derivative of e to the minus kt times the derivative of the inside. You guys all good with that? Okay. And then what happened to the TE?
It's a constant.
Yeah, the derivative of TE is 0, right? Because it's a constant. Okay, so you got this. So my differential equation, right, says I should question, is this thing? So T0 minus TE times minus K e to the minus KT, is that, what do I need over here? That. Good. A minus K, and then a T, which is that whole business. Yeah, and so this is why I'm doing these up here, right? It's like the first few examples, you're like, oh, jeez.
No.
Right, so you just very carefully have to plug everything in, and sometimes it's really messy. So I got, is this T?
You need a plus.
No, I need the plus TE. Okay, so now this whole object, and I would kind of recommend that you do this a little bit for the first few. Like mark down what things are so that you don't end up losing little bits and bobs.
Are we gonna have student graders for the homework?
No. Your homework's not going to be
It
great.
could be
Great
easier for them
homework.
if we did that too.
Yeah, that's a great idea, actually. What else do I need here? So I had, in the parentheses, should have been T minus TE. Okay, so, and again, these are equal up to some algebraic manipulation, right? Or trigonometric identity, whatever nonsense. In this case, it's pretty easy, right? The TE's cancel. And this thing and that thing are equal because multiplication is convenient. Good answer. Okay, so check. And so ultimately, is the t that I found a solution to my differential equation?
Yes.
Yes.
A solution.
Does this thing now work in all cooling situations?
Not at all.
Oh,
No.
No.
Does it work in situations where you can reasonably say the set of assumptions we made when we wrote this thing down?
Yes.
Yeah-ish.
Ish.
At least. Everything in differential equations land tends to be an approximation. So a good ish at the end of all your problems is probably a good idea. Cool? Questions, things? Certainly, mathematically, this differential equation has exactly this solution. You guys see that? Mathematically, this is actually the case. This thing solves that. Whether that's good for your model or not, or good for the world, is kind of an open question. It might be that when you wrote the model down, right, when you wrote that differential equation down, you made some basic misunderstanding of the way the world works. That happens all the time. Like, models are not always good. The math here is awesome. Whether that's a good situation for the thing you're dealing with, I don't know. Depends. Cool? Questions, thing?